Hey everyone, in this video I'm going to be going through the solution to an old BMO1 combinatorics problem. So this is BMO1 2000, question 5. Now this is actually not a super complicated problem. It's one of those classic ones involving like putting people into teams and so on. But why I think it's quite cool is that I'm going to present 3 different solutions which sort of reuse some of the same ideas, but they are definitely different approaches. And in doing so, I'm essentially going to equate 2 different quantities and deduce a more general result about problems of this kind. So I'm doing a technique called double counting. So a really good example of double counting is, let's say you want to show that multiplication of natural numbers is commutative. So for example, that means n times m equals m times n, where m and n are natural numbers. So the way to do this is you draw a square that has basically, say it has n columns and m rows. So what you can do is if you want to count the total number of sort of cells in the grid, you could just either you could count in terms of rows or you could count in terms of columns. And you can say, like, for example, there are m rows and then in each row there are n cells. Or you could say that, you know, in each of the n columns there are m cells within each of those columns, and then so that's how you, and of course because the total number that you're counting, which is the number of cells on the grid, is the same, so therefore you can equate the 2 expressions. So I'm going to be doing a slightly more sort of non-trivial example of this. So basically what we have, so often they'll phrase this in a very verbose way, a bunch of dwarfs, some quiz, blah blah. But basically what we have is we have 7 distinct objects. 1, 2, up to 7, and so to show that they're distinct, I've given them, you know, I've labeled them 1 up to 7, and then basically you want to put them, you want to partition the set 1 up to 7 into 4 non-empty subsets. So that means in the context of the problem, you have 4 teams, and you don't care about the order of the dwarfs within each team. So that means it's just basically like a partition, and you only care about the kind of subsets themselves. And then the order of the teams don't matter in the sense that the subsets are kind of like they're not ordered. Basically, that's what it means. And then each of the dwarfs must be placed in exactly one of the teams, so that means each of them are non-empty, each of the subsets. So basically, you want to find out the number of ways of achieving this task. So I'm going to present. And in the last part, you have Snow White agreeing to take part. So that's basically just you do the same, but you add an 8th element to the set here, and then it's basically the same idea. So we want to think, as I said, I'm going to show you 3 different solutions. The first solution is perhaps, I think, potentially the easiest. So I think it's the easiest in terms of ideas, but there's quite a lot of computation, which is, I suppose there is also computation in the other 2 solutions. But in this case, you know, I think there's a lot of just like arithmetic. So this is basically, what I'm going to do is I'm going to construct a recurrence relation. So first, I'm going to introduce some notation. So I'm going to say that the quantity UNK is basically, it's what you might expect. It's the number of ways of partitioning 1 up to n into k non-empty subsets. So yeah, there's supposed to be k of these. And okay, so in what we're interested in finding is U74. And the way we're going to do this is by, as I said, constructing a recurrence relation. So first, I want to relate basically values of u and k to kind of smaller values of n and k, and see then if I can kind of recursively. So if I can solve this problem for like really trivial cases, for small values of n and k, and I can basically build up. I can just do some sort of multiplying and adding and get U74. So suppose then we want to find u and k. Well, I suppose if we consider the nth object, or in this case it's like the 7th dwarf, there are basically, I guess there are 2 possibilities. So the first possibility is that the nth item is sort of in a subset of its own of size 1, and then in that case we're left with, well, we have n minus 1 remaining distinct objects. We want to partition those into k minus 1 subsets, right? Because then that just forms in total, that forms k subsets with n objects total. So this is u n minus 1, k minus 1. Or we can have the nth object being in one of the other. So it belongs to basically it basically shares a subset with something else. So in that case, we have k subsets total. Well, we can put the nth object in any of the k. So that means that there's going to be, because there's k choices, u n minus 1 k minus 1 u n minus 1 k, sorry. And the n minus 1 here is because there's n minus 1 objects remaining. So I think if I didn't explain that clearly, let me just do an example. Let's consider U74. So in one case, we have, for example, so this is where you want the seventh dwarf to share a team with the other dwarfs. So you could have, say, a team of two here, a team of one, and a team of one. So if I can count, that makes 6 in total with 4 teams. And then now the seventh dwarf, we can basically place it in any of the teams. So either we can place it here, 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 or here. So this is dwarf number 7. And so this corresponds to the second case. And then, of course, the first case is when it has its own, the seventh dwarf has its own team. So what I showed on the previous one is that basically unk is equal to un minus 1 k minus 1 plus k times u n minus 1 k. So we want to find u74. So this is supposed to be u63 plus 4 times u64. Okay, and then what we're going to do is we're just going to keep sort of iterating this until we can get until we reach. So I think putting them n dwarfs into 2 teams is probably quite easy. So let's just keep going until we end up with a 2. So in this case, this is going to be, I'll put this in a bracket. So this is u5, comma 2 plus 3 times u5, comma 3, I believe. Yes. And then in the other case, this is 4 times u5, comma 3 plus, if I can count, it's 4 times u5, comma 4. Yes, that is correct. Okay. And of course, so as you're going to see, u5, comma 4 is pretty straightforward to do, as you'll see in a second. So basically, what we want to find then is, so this is now u5, comma 2 plus 7 times u5, comma 3 plus 16 times u5, comma 4. Okay, so now u5, comma 2. So basically, we have 5 objects, and we want to put them into 2 teams where the order of the teams don't matter. Well, you could just think then of, let's say we have 1 up to 5. We can just consider any non-empty subset or any like non-empty proper subset, so it can't be the whole thing. So for example, if we had 2 and 3, well, we could just put 2 and 3 as one of the teams, and then everything left over we can just put in the other team, right? So that would be 1, 4, 5. That would just go in the other team, right? So basically what we want is, all we have to do is choose a non-empty proper subset of 1 up to 5. So you know that there are 2 to the 5 minus 2 of them, because in general there's 2 to the n subsets of 1 up to n, and then we're excluding the empty subset and the whole thing. But we're not quite done yet, because that just determines the left team, but since the order of the teams don't matter, we have to divide by 2, because otherwise we double count, for example, when we choose 2, 3, and when we choose 1, 4, 5. So this is now 32 minus 2 is 30, over 2 is 15, so this should be 15 the first term here. And then I'm going to do the recurrence relation again to find u5, comma 3. So u5, comma 3, this is equal to u4, comma 2 plus, and then so this is k times, so in this case 3 times u4, comma 3. Okay, and then as for u4, comma 2, but it's exactly the same argument as 1 up to 5. So this is 2 to the 4 minus 2, which is 14 over 2, which is 7. And then you have 4, comma 3. But 4, comma 3, if you think, so what this basically, the only way to put 4 dwarfs into 3 teams where they're non-empty is, well, you have to have a team of 1, a team of 1, a team of 1 to start with. And then basically it's just, you just decide which 2 dwarfs are going to share a team. right? Because the only way, sorry, so this should be a 2. So the only way to do it is 2, 1, 1, a team of 2, team 1, a team of 1. So you just decide which of the dwarfs are going to be together. So that's just 4 choose 2, which is 6. So it's plus 18 is 25. So this is plus 7 times 25. And then finally, the last thing, so by the same argument, if you have, say, if you want to put 5 dwarfs into 4 teams, you just decide which are going to be the 2 dwarfs that share a team. So that's 5 choose 2, so it's 16 times 10, and this is equal to 350 in total. Okay, so I'm not going to do the bit involving Snow White because it's pretty much the same argument. I'm not going to do it for any of the 3 solutions, but you can try and find it yourself and leave a comment if you've got the answer. So now my second solution, so this is a solution which is quite quick to do in the Olympiad, and because of the numbers in the question, it's like it's actually quite an easy solution to write up, and it's not very long, but it doesn't really generalize that easily. And you can see how for larger values of n and k, it's going to be like kind of a bit problematic to do. And then the third solution I'll show you is I think probably the most like kind of combinatorial one in spirit, and it's the one that generalizes very easily. So the second solution is basically what we observe is, so we want to find U74. Well, let's just think, what's the largest possible size of a team? So there can't be a team of 5, for example, because if there's a team of 5, you only have 2 dwarfs left over. So even if you did 1 and then 1, that's only 3 teams, and there has to be a team of 0, which is not allowed. So the largest team then, it's either, of course, similarly, the largest team can't be 1, because you only have 4 teams. So the largest team is either 2, 3, or 4. So in the case where the largest team is, let me just put this in red just to show that this is not allowed. So if the largest team is 4, then the only leftover possibilities are 1, 1, and 1. So basically what you need to do is just choose 4 dwarfs out of 7 and then put them in a team of 4. And then all the remaining ones, they just go on a team on their own. And of course, this is using the fact that the order of the teams don't matter. So this is 7 choose 4 ways. And then the next way, so if the largest team is 3, then, okay, we put a 3 here, and then are we allowed to have another 3? No, because then that will be 3, 3, and then 1, but we need to have 4 teams. And then similarly, we can't have 1, 1, 1, because that only adds up to 6, so we must have a team of 2. Okay, but then now we have 2 teams left over and 2 dwarfs, so we can only do 1 and then 1. Okay, so how many ways are there to do this? Well, we just choose 3 dwarfs to go in the team of 3. So that's 7 choose 3. And then now we have 4 dwarfs left over, and we just need to choose 2 of them to go in the team of 2. So this is times 4 choose 2. So this is equal to, so 4 choose 2 is 6, and then 7 choose 3, I think it's 21. Hopefully, if this doesn't give the right answer, then I'll go and edit this part of the video. And actually, so 7 choose 4 is also 21 as well. Okay, and then, let's just leave this for the moment, and then let's hope it adds up to 350. So then the next team, so if there's a team of 2, largest is 2, well, we can't have 1, 1, 1, so we have to have another 2. Okay, but then now there's 3 left, and there's 2 teams, so we need to have a third 2, and then a 1. Okay, so now you might be tempted to think then it's going to be 7 choose 2 times 5 choose 2 times 3 choose 2. So the reason being that you start with 7, you choose 2 to go in the first team of 2. Then you have 5 left, you choose 2 to go in the second, and then you have 3 left, you choose 2 to go in the third. But then, of course, now, because the teams of 2 they're supposed to be, because the order doesn't matter, so this is why you have to divide by 3 factorial, which is 6. So no, you don't have to do that in the first case, because when you choose the 7 to go in the team of 3, there's no chance of there's no chance of double counting, because the team of 3 is always distinct, kind of combinatorially speaking, from the team of 2. Whereas in this case, for example, you could choose say 1 and then 6. 1 and 6 to go in the first team of 2, and then you choose like 3 and then 5, and then a bunch of others, and then the next time around you come and choose, you could end up choosing 3 and 5 for the first one and 1 and 6 for the second one, and then of course you choose the same ones for the last 2 teams, let's say, and then of course that's double counting, so this is why you have to divide by 6 in this case. And yeah, to be honest, I actually I can't be bothered to do the arithmetic, but just trust me that it gives you 350 as the final answer. Okay, so I think the last solution is the most combinatorially interesting. And I'm going to use something called the inclusion-exclusion principle. So let's first pretend, in order to make the problem much easier, let's pretend firstly that the order of the teams does actually matter. And let's also pretend that we allow some of the teams to be empty. So this problem is way easier to solve than the one we're asked to do. So in this case, well, each of dwarfs 1 up to 7, they have 4 choices of teams. So there's just going to be 4 to the 7 total. And these are all genuinely distinct because, for example, if, say, dwarf 6 chooses team A instead of team B, that entire configuration is different because the order of the teams matters. So, okay, so we want to try and recover the original problem. What I'm going to do is at the end, I'm going to worry about the order of the teams. Because let's say I'm able to find the total number of teams where you don't allow any of the teams to be empty. Then I can just divide by 4 factorial, or which is 24, in order to get the answer I want. This is when you stop distinguishing A, B, C, and D. Okay, so let's think. So I guess we need. We started with 4 to the 7. And I want to figure out, I want to get rid of all the possible configurations where any of the teams are empty. So, well, of course, let's suppose at least one of the teams were empty. So we would choose then a team to be empty, right? So we can choose A, B, C, or D. So we're minusing 4, choose 1. And then suppose then we've now, for example, we've put A to be, we want A to be empty. Well, then now there's 3 choices for each of the 7 dwarfs. So that's going to give you 3 to the 7. But we're not quite done because we've basically overcounted quite a few of the configurations. Because, for example, let's suppose we chose one of our 4 choices, 4 choose 1 choices, which is 4, was to choose A to be empty. And then it turns out that in a certain configuration, B was also happened to be empty. So all the dwarfs chose C and D. Then that same configuration will be counted again when we choose B to be empty originally. And then it just so happens that A is empty. And then all the dwarfs go in C and D in the same places that they went initially. Then they went in the other case, if that makes sense. So we actually need to add back on the cases where at least 2 of the teams are empty. So how many ways are there to do this? Well, there's 4 choose 2 ways because you choose 2 of the teams, say A and C. And then now there's 2 choices for the dwarfs, and there are 7 dwarfs, so it's times 2 to the 7. And then, okay, but then again, by the same logic, we've now overcounted the case where at least 3 of the teams are empty. So we now need to minus 4 choose 3. And then this is times 1 to the 7, because now the dwarfs only have 1 choice. They just go in the team which is chosen to be non-empty. And then, of course, we can't have all 4 empty because we need to put the dwarfs. Each dwarf has to go somewhere. So this is the answer. And then, of course, now we need to divide by 4 factorial. So it's 1 over 4 factorial times this. And again, I can't be bothered to do the arithmetic, but you should just trust me or use a calculator, and you know that it's 350. But what we've actually managed to show more generally is the following. So what we did is at the start of this problem, we introduced a quantity called un, k, which is just to summarize, it's basically if you have n distinct objects and you want to partition this set of n distinct objects into k unordered non-empty subsets. And then basically the number of ways to do that is UNK. So in the first part of the question, we found a way so we found basically a recursive or inductive definition of UNK, right? So this was saying that it was UN minus 1, K minus 1, plus K times UN minus 1, K. And then it turns out at the end, we actually were able to find a closed form expression for UNK. So we did this in case U74. I'm actually just gonna copy this, copy and paste this, but just to make sure, just in case I make a mistake. So this is the expression. This is the closed form expression. So, and the reason why is it's exactly the same argument as for 7-4, just generalized, where instead of thinking about 7 dwarfs and 4 teams, you think about n dwarfs and k teams. It's exactly the same argument, and you end up with this expression here. So I think that's quite nice. We sort of what we did is we did sort of double counting. So we did 2 different ways of counting the same quantity, and then of course because we count the same thing, we can equate them. And so this quantity here, UNK, is actually known as the Stirling numbers of the second kind. So I'll write this as a Stirling 2. So there's also Stirling numbers of the first kind, and you can Google those if you're interested in knowing what they are. And and usually the notation that's often used for this is it's a square bracket nk. So this kind of looks like the binomial coefficient, but it's a sort of curly bracket instead of like a normal bracket. And okay, well, yeah, that's pretty much what I wanted to say. So thanks very much for watching, and hopefully you found this interesting, and I will see you in the next one.